Hello, today we continue our topic exponential functions, but we study such functions to different ways other than e. And at the end of the video, we study some applications. We know about the function e to the x, right? E to the x, where is the number such that the integral of 1 to the e dx over x equal to 1, right? Or that is ln of e. So that is just a number, right? A very special number, and then we already saw some properties of such function e to the x. And now we want to define some exponential function to the base that different to e, that different to e. So how? Suppose that I have some number a bigger than 0, okay? I want to define something like y equal to a to the x, okay? So we need to find the way to do that, okay? So suppose that we have a greater than 0, and suppose that we know, we could determine, we could define this function. Does that make sense? And now let's try to see what happens if we have y equal to a to the x. Because we never know, right? What is a to the x? But suppose we know that. Suppose we have that. So what happened? From this, if I apply the natural log to both sides, so I have ln of y equal to ln of a to the x, right? And since we have natural log in here, we can take the power down right here, okay? So I have the following one. This is just equal to x, ln of a. Everything is good for me. You know why? Because a is a positive number. I can determine ln of a. So that is just a number, constant, right? That's just a constant. X is variable, that's fine. All right. Now, I want to find a, right? No, I want to find y. I want to find y. From this identity, I will apply exponential function. So I apply e to ln of y. I will get e to the x ln of a. The right hand side part is well defined, right? The left hand side part is also well defined, because you know that is just y, right? We know that e ln of y is just y. So I have y equal to e x ln of a. You see, interesting. We start from the y equal to a to the x, right? And finally we got y equal to e to the x la. So what does it mean? That means I can define the function y equal to a to the x as a to the x equal to e x la. Okay, so we will take this as the definition of the function a to the x, the exponential function to the base a, where a is a positive number. Okay, so using this definition, the exponential function y equal to a to the x has the following property. If you have 0 in here, you have a to 0 is just 1, right? Why? It's obvious, you know, from here, you plug 1 when you plug x equal to 0, right? To this part, you get 0 times LA is 0. E to 0 is just 1, okay? Second property, if you have a to the x and you multiply with a to the y, you get a to the x plus y. This comes from the property of the natural exponential function. So I think we can check it yourself. 3, you have a to the x over a to the y, that is a to x minus y. So this also a very similar property of the natural exponential function. You convert, right? Exponential function convert, the difference into fraction or into a quotient, you see, and convert a sum, right, into product. You see that? Okay, next, if you have a to the x and then you apply one more time, right, you get a to the x times y. So all these four properties are important for exponential functions. And then forget that we may define exponential function for a greater than 0. Okay? Let's consider the following application of exponential functions. Radioactive half-life model. The half-life of carbon-14 is about 5,715 years. We have a sample that contains 1 gram of carbon-14, and the question is how much will be present in 10,000 years. Okay, so we need to find a model that helps us to find the amount of carbon-14 in 10,000 years. We suppose that, at the time t equal to 0, so we have 1 gram. Okay, and it says half-life, the half-life of carbon is about 5,715 years. That means when t is equal to 5,715 years, we still have 1/2 grams. Okay, so we need to find the function. We need to find the function, and in this case, I would like to use exponential function with the base 1/2. With the base 1/2, that means I pick a equal to 1/2, and I consider the function y equal to 1/2 to t divided by 5,750. Why we need to divide by this number? Because based on this observation, if you put t equal to 5,715, you get exactly 1/2. And now if you want to see how much will be present in 10,000 years, you just plug t equal to 10,000 into this function. You get y equal to 1/2, 10,000 in here divided by 5,715, and this is approximately equal to 0.3 gram. Okay, so that's how we can use such function in this model. All right, now let's talk about the graph of this function. Why we can use such model, for this. Okay, this is kind of decades. You see, it's interesting, right? So let's talk about this. I want to graph the function y equal to 1/2 to the x. But what is this? This is 1 to the x over 2 to the x, right? By the property of exponential functions. And on the top we have 1, in here you have 2 to the x, or you can write that is 2 to negative x. That is 2 to negative x. Agree? Why? Because what is 1? 1 is 2 to 0, right? 1 is 2 to 0. So 2 to 0 over 2 to the x equal to 2, 0 minus x, which is 2 to negative x. Okay, that means if you want to graph this function, okay, we need to graph this function, right? But interestingly, the graph of this function can be obtained from the graph of this function 2 the x. How? Because the graphs of this function and of this guy are symmetric with respect to the y-axis. I hope you still remember that, right? Like in general, if you have the function f of x, right, you may find the graph of function 1 of negative x. You know, those graphs should be symmetric with respect to the y-axis because you just change from x to negative x. You see, so basically you change, right, from x in here, you move to this point, but you still keep the y. Is it correct? So you know, that's how we can do that. Agree? All right, so let's graph the function y equal to 2 to the x, and then we take the symmetry, right, with respect to the y-axis. So for this, I just give a sequence of values. Let's say -2, -1, 0, 1, and 2. I have 2 to the x is 1/4. Here's 1/2. Here's 0, 2, and 4. Okay, you may choose, you know, more than 5 points, but I think that's okay for us. And then I will plot those points x, y in here. X equal to 1, y equal to 1 in here, x equal to 2, y equal to 4 in here. Okay, let's zoom that out. No, equal to 2, sorry, when x equal to 1. 1, 2, 0. Let me erase this. And then when x equal to -1, so I have 1/2. That is 1. That is 2. That is 4. When x equal to -2, that is 1/4, right? So 1/4 is right here. So I will have the following point. Let's say this point, say this point, this point, this point. Now you connect them. Okay, I'll connect them. I'll have a graph. Don't forget we have point right here. Okay, you see, this is the graph of the function y equal to 2 the x, and from here I can make the graph of the function y equal to 2 to negative x. You see, we just change, right? So they are symmetric with respect to the y-axis. So I have this point, at this point I have this point, I have this point, and I have, you know, something in here, this point. So basically I will connect them. You see, I have this, 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 this. Okay, and of course we have something like here. And in case, you know, in our problem, the t is x, right? T is x. So if t approaches positive infinity, of course, you know, and the amount of carbon 14 is just go to 0, right? You see, go to 0 right here. Is that correct? So, you know, such function can be applied really well in such situation. All right. Now let's talk about logarithmic functions to the base a different to e. Because you know ln of x, right? And we have e to the x. Of course, they are inverse of each other. We just use ln to determine a to the x, right? We know how to find a to the x. That is e to x ln of a. So, and we have seen that actually if you differentiate this function, right? If you differentiate this function, you see that actually this function is increasing. Why? The derivative of this guy is nothing but, you know, e x ln of a times what? Times ln of a. So I want to take my works back, right? About increasing. Look at this. It really depends on a. I'm sorry for that. So if we have a bigger than 0, the function is increasing, right? Because ln of a in that case is bigger than 0. Do you remember that property? So we know the property ln of x bigger than 0 for x greater than 1, yes, and ln of x less than 0 for x between 0 and 1, right? In this case, if a is bigger than 0, bigger than 1, sorry, oh my goodness, bigger than 1, then ln of a bigger than 1, bigger than 0 again. So in that case, this guy, the derivative is bigger than 0, right? The function is increasing. But if a is between 1 and 0, the function is decreasing, right? Because ln of a is less than 0. But in both cases, the function is monotone. The function is monotone, right? So what does it mean? That means that is 1 by 1, right? It's 1-to-1 function. So the function has an inverse. That is what we need, okay? That is what we need. A to the x has an inverse. Okay, so how to determine that inverse? I would denote this inverse by what? By log a to the x. And that's how we can determine logarithmic function to the base a. Okay? So similar to the case, to the relation between e to the x and ln of x. E to the x equal to y if and only if x equal to ln of y, right? In this case, we also have a to the x equal to y means x equal to log to base a of y. So that is how, related such functions. Okay. All right. So, and from here, similar to the case of the natural exponential function, the logarithmic function to the base a also has some very good properties, like you have a to log ax equal to x, right? If x is greater than 0, and another one is log a to the x, this is also equal to x. So these two properties comes from two identities of inverse functions, because we know exponential function a to the x and log to the a, right? They are inverse of each other. So when you apply a to the inverse, you get identity, means x. When you apply log to exponential, you get also x. Agree? So those properties are really simple and really, really similar to the case of the natural logarithmic function and the natural exponential functions. Now let's consider some examples. Let's solve the following equation. A to the x equal to 1 over 81. 81 in this case, very good number. Why? Because, we know exactly 81 is 3 to the 4, right? So means, you change the right-hand side to get the form 3 to the 4. With the negative in here because we have 1 divided by 81. So if you compare 3 to the x and 3 to negative 4, so x should be equal to negative 4 because we know the function is monotone, right? So that means, we may not have two numbers such that, the function values equal to 3 to negative 4. So you got x equal to negative 4. But in general, if we don't have like 1 over 81 right here, we need to apply the exponential function, because here you have exponential function, right? We need to apply the logarithmic function because we want to cancel them out. If you have exponential function, you apply logarithmic to cancel that out, like this. Okay, so I have ln, but I choose the base 3, okay? And here I have 3 to the x. And that is equal to log base 3, 1 over 81. Okay. On the left hand side, I have x. That's what we have in here. Okay. On the right hand side, I have log 3, 1 over 81. And of course, you can use calculator or whatever. But in this case, we should have -4. Agree? If they give you a logarithmic function, so how to do that? Like log to the base 2x equal to -4. So you need to apply the inverse function of logarithmic, which is the exponential, right? So you apply the exponential to both sides, but the base should be the same with this guy, right? You have 2. So I have 2 log 2x equal to equal to 2 to -4. But the left hand side is equal to x, and this is equal to 2 to -4, which is 1 over 2 to the 4 is 1 over 16. Okay, now let's talk about differentiation and integration of such functions. Okay, let's talk about differentiation first. Again, from the definition of logarithmic functions and exponential functions, we have the following formulas. I have a to the x, derivative is ln of a times a to the x. That is the first one. The second one, a to the u, so you have the chain rule, a to the u times ln of a times u prime, right? The chain rule. Second property, log to the ax derivative is equal to 1x, but we have ln of a, if a is the e, right? So ln of a is just 1, so you have 1 over x. That is the derivative of the natural logarithmic function. Okay, so similarly we also have, okay, let's say this is 3, that is 4. You have the chain rule, so that is 1, or let's say u prime over ln of a times u. Again, right, please make a formula sheet for yourself. Okay, and you can see the proof of these formulas in the textbook. They are pretty easy. Let we move to examples. Let's find the derivative of the following function. First function, y equal to 2 to the x, right? We just saw that. We just graphed this function. So by the formula, we get y prime equal to 2x and then ln of 2. So if you remember, right, we have the natural logarithmic function and natural exponential function, e to the x. The derivative of this guy is itself, right? Because if the base is 2, right, so you have, if the base is e, so you have LE of e, which is just 1. But if you have different base, you still have this value. Okay? Let's say, let's find the derivative of the following function. So we need to use the chain rule, of course, and the formula right here. So y prime is equal to u prime, means cosine of x prime divided by ln of 10, right, times cosine of x. The derivative of cosine is negative sign. And here I have ln of 10 times cosine. So you can write in short that is -1 over ln of 10 times tangent of x. Okay. Next problem. This function is more complicated, but that's fine. We will have chance to work with this is square root of 5, x plus 5. No, we have chance to recall some properties of logarithmic functions. So when we study the natural logarithmic functions, we know that logarithmic functions convert quotient to difference, right? And product to sum. I hope you remember that. And we solve some problems how to rewrite such complicated expression into simpler one. Means we can break that expression into simpler formulas, right? Everything on the top will be with the positive side. Everything in the bottom will be with the negative side. And if you have power, you can take the power out of logarithmic functions. So in this situation, I will apply that property. Okay. First, I need to break this into different functions. Okay, let me write right away, right? And then I will explain you. We have log of x, right? With the base 3. But what is the power of x in here? The power is 1 over 2. So I write 1 over 2 in here. You see this? And then in the bottom we have x plus 5. So I write negative log x plus 5. That's it. Agree? Then you can differentiate each term easily, right? It's easier than differentiate the whole thing in here with the chain rule, right? So I have y prime equal to 1 over 2, the derivative of log x. Okay, I don't remember that. I need to check it. It is right here, 1 over ln of ax, right? So a is 3. I have 1 over ln of 3 times x. Okay. Second one, I have, here I have 3, sorry. I have 1, the chain rule, but the derivative of x plus 5 is just 1, okay? X plus 5 derivative is 1, that is u prime. So I have 1 over, again, ln of 3 times x plus 5. You see? If you want, you might simplify that, pretty easy. Look at this. I can, take 1 over ln 3 out because that is just coefficient and common coefficient, right? In here I have 1 over 2x minus 1 over x plus 5. Okay, if you want to make that more beautiful, you can write x plus 5 minus 2x over 2x x plus 5, that is common denominator. And finally you get 1 over ln 3 in here, 2x x plus 5 and negative x plus 5. The reason I show this because sometimes you need to solve y prime equal to 0. So we saw that several times when we need to find extrema of functions. All right. Now let's talk about integration of exponential functions. So since we have derivative of a to the x is equal to a to x times ln of a, from this we integrate both sides, we get this formula. Okay, of course, a should not be 1, right? Because if a is 1, so there's nothing to do, right? Example, we can find antiderivative of 2 to the x dx. So by this formula we have, this is just 2 to the x ln of 2 right here, okay, and plus c. It's pretty easy. Or sometimes you can convert everything into ln, okay? So I don't think that we need to do more examples on this. The last part of this lecture is applications of logarithmic and exponential functions, okay? when we study logarithmic functions, let's write in general form logarithmic to the base a of x, right? Logarithmic function has very good property. If you apply a log to some function like that, or you can write log to the a f of x to the g of x. So you can take the power down. You can take the power down here, okay? So this is just gx times log a f of x. Or this case just, n log to the a and x. So this is very good. Um, sometimes you have such function like y equal to x to the x, right? It looks very strange, but it is still a function. And you need to find the derivative of this function. Okay? Let's find the derivative. We don't have any room, right, to find the derivative of this function because you have x to the x. If you have a to the x, yes. If you have x to the a, yes, I know how to find the derivative of such function, right? But now x to the x. So we need to apply the logarithmic functions in this case. If we apply both sides, apply ln to both sides, right? So I get ln of y equal to ln x to the x. And this is x ln of x. Of course, we consider the case when x greater than 0, right? And now you can differentiate both sides because, we have x and ln x. That is just product of two functions, and we know how to differentiate each of them, okay? And here we also have two functions, so we need to use the chain rule, okay? So now I differentiate both sides. Okay, let's say differentiating both sides, we get on the left hand side I have y prime over y, right? The chain rule. On the right hand side I need to use the product rule. Derivative of x is just 1, so I write ln x in here plus x. Derivative of ln of x is 1 over x. This is ln x plus 1, right? From here I get y prime equal to y times ln x plus 1. But we know y, right? So that is just x to the x ln x plus 1. Okay? We use this a lot. I'll tell you this, right? When we study some very special forms of limits, we will turn back to this topic. We will learn how to use logarithmic function for such, functions. Now, let's talk about compound interest. Okay, that is very important application of exponential. Compound interest. Right, now let's talk about compound interest. Suppose that you have P dollars. You want to put this into a bank account, okay? To a bank account with the rate R, okay? And you are interested in what happened in your account after a year, okay? Means you want to find the balance in the account at the end of a year. So, in order to solve this problem, we need to know how many times in a year the interest is compounded. Because that is important, right? So you need to find for the time, n is the number of time that the interest is compounded. Otherwise, we cannot find the balance in the account at the end of the year. Look at this picture. So now we have P, right? Let's say, let's consider the simple case, just one time. That means the interest is compounded annually, okay? Let's consider this case, case one. The interest is compounded annually. All right, so what does it mean? That means, after a year, the amount would be P times 1 plus R. Is that correct? Because that is P plus PR, where PR is the interest, right? So, in this case, you just write P times 1 plus R. If the interest is compounded annually and just one time, okay? I mentioned in here means, one time. All right, so what happens if the interest is compounded semi-annually? Let's consider case 2. The interest is compounded semi-annually. That means 2 times, right? 2 times. So in that situation, this is the beginning, right? P, and then after 6 months, let's say 6 months in here, the interest compounded one time. So in this situation, I will have P1 equal to P, right? Plus P, but R over 2. You see that? Because, R is the rate for the whole year, right? So for 6 months, that is R over 2, just a half of the rate. Is that correct? And then after 6 more months, right, I can find the amount in the account, but based on P1. You see that? So I can write that is P1 plus P1 times R over 2. Again, right? So that is the total amount you have at the end of the year. Let's write this down. For this, I have P1 plus R over 2, right? And we plug this into the formula of P2. But before that, I need to factor P1 out. I get 1 plus R over 2, right? And P1 is P1 plus R over 2 times 1 plus R over 2. That's why you have P1 plus R over 2 squared. Look at this. If the interest is compounded annually, means one time, you have this formula, P1 plus R, okay? If the interest is compounded 2 times, that means semi-annually, so your amount in the account would be P2 equal to P1 plus R over 2 and then squaring here. So using this observation, you would guess if the interest is compounded n times a year, right? The interest is compounded n times a year. Then at the end of that year, you would have the following one. Let's say Pn, right, equal to P1 plus R over n to the n. You see, the situation is, easily generalized. So whatever you want, right? And maybe 12 months and maybe 365 days, or maybe, the interest may be compounded by hour, right? Hourly. So it really depends on n, right? And how the interest is compounded. It's just funny, if you pay attention, and if you use credit card, sometimes you forget, right? Sometimes you forget to pay the credit card, and and I guess the interest for mixed, balance would be compounded by daily. So you may think, yeah, uh, if n is increasing, right? This function is also increasing. How do you think about that? The Pn is increasing. That means if the number of times when the interest is compounded is increasing, then the amount also increasing, right? So, in case if you need to pay credit card, so you need to pay more than that. I hope you understand the game, right? Between us and the bank. So what happens if we consider the limit of Pn when n approaches infinity? That means the limit of what? Of P 1 plus R over n to the n. When n approaches infinity, but P is constant, so we can take that out. We have limit in here. 1 plus R to the n and n approaches infinity. So what is the limit of this guy? This limit is equal to P e to R, where again, right, R is the rate. You see, interesting, right? And that's how we can move from discrete case. This is discrete case. I can say that. Discrete case to continuous case. Why this case is continuous? This case is continuous because the interest is compounded infinite time, right? A year. You see? That means, if n is just a finite number, you have a discrete case. Is that correct? But when n increases to infinity, your interest is compounded infinitely time. So that means, that is kind of, continuous, right? Look at this picture. So here's 12 months, right? From 0 to 12. So if you have 12, it's okay, right? But you have, you divide it by just twice a month. So you have smaller interval. You see this? So that means, if you increase the number of sub-intervals n to infinity, so you will fill all the whole interval in here. So you get a continuous case. Does that make sense? All right, so how did we get this formula from here to here? In this case, we need to use a very famous limit. And this famous limit look like limit of 1 plus 1 over x to the x when x approaches infinity equal to limit of x plus 1 over x to the x approaches infinity equal to 2e. Okay, so usually you can see this form. It's rarely to see this form, and this is e. So yeah, if you compare this formula and this formula, the difference is only in r. You see this in r, and because of that you have e to the r right here, because this limit is equal to limit of what? Okay, let me write P in here, limit of 1 plus n, 1 over n to the r. You see? And here you have n to the r times r. If you group this all together, so you get number e by this limit, and then take the power, you get e to the r. Okay? To finish this video, let's consider the following example. A deposit of 2,500 is made in an account that pay an annual interest rate of 5%, okay? And they ask us to find the balance in the account at the end of 5 years when the interest is compounded quarterly. All right? So quarterly means, 4 times a year. But now we have 5 years, right? That means the number of times is 4 times 5 is 20. Means n in this case is equal to 20. All right? So if you apply that formula, let's copy that again. A is equal to P 1 plus R over N. In here you have NT. You have the following one. P is 2,500. 1 plus R is what? R is 5, right? So I can write 0.05 divided by 4 because quarterly, right? And here you have 4 times the year is 5 years. T is the year, okay? The number of years. So, you just need to use the calculator, right? And you can find this is approximately equal to $3,200, $5.09. Okay, so in case if they change the plan, right? In case if they change the plan, say yeah, the interest is compounded semi-annually, so you just need to change the number n in this formula and in this case. That's it. Okay, so I hope that the video is clear enough, but if you have any questions, please feel free to let me know.